please. Okay, so that's the test prep. Let's learn. Polar is a significant part of top 2. Do you remember your polar? Okay, well, good news for you is that the review of what you have learned is actually spread over several different lessons. Today we'll do some of it. All right. So we're going to do the whole page, but set 107 is polar, set 110 is polar, set 119 is polar, and then calculus of polar is like set 120. Okay. All right. So here's the deal. First basics is understanding what in the heck polar is. When I give you directions to a point in two-dimensional space, you could give that directions to that point by saying, hey, go this far horizontally and this far vertically. We call that the Cartesian plane, named after Rene Descartes, who was first and foremost a great philosopher, but also a great mathematician on top of it. Okay, the Cartesian plane, for whatever reason, Saxon has continuously called it the rectangular coordinate plane. I guess he hates Descartes. Anyway, the idea on this is that you're given horizontal and vertical directions to get to a point. Yeah? Now, in order to make locating that point easy, they typically give you a space that has horizontal and vertical breakdowns, yeah? So that's why on a normal graph, what you would probably call a normal graph, you'll see horizontal and vertical lines because that's how they're giving you directions to it. It is, however, also possible to get to this point by saying, instead of what's called taxicab geometry, which is to say you have to follow the streets, you have to go this far west. You could get there by being a bird. If you wanted to get to that place being a bird, obviously you wouldn't follow the streets. You would just point in the direction you wanted to go and go there. Now that's polar. Polar is as the crow flies. Think of it like a bird. It depends on you turning in the direction you want to go, and then going either forward or, crazy enough, you could also back up to get to a point you want it to go. All right? Now then, it's important to me that you understand that though this graph looks crazy, it's still the Cartesian plane. This is still x, and this is still y. And you might think, well, it doesn't make sense. It looks totally different. Well, of course it looks different, because to get directions polar style, it's not going to help me to say, hey, if I go out 5 units to have this horizontal grid, if I want to get to this place in space, I need to have markings that tell me how far from the origin I'm going. And that means concentric circles to show 1 unit out, 2 units out, 3 units out. So it stands to reason that the direction markers on polar are going to be different because you're getting places differently. But it's still the x, y plane. Understood? Okay, it's just a different direction system. All right, now, when I get to this point in space, in x and y type, how many ways to get me there? How many accepted ways to get to a place in coordinate space? Is there another way to write the point 3? There is none. There's exactly one way. X, then y. In polar, however, you can get to any point 4 different ways. And you need to be familiar with all 4, because sometimes equations give you 4. One is to go, now you always turn first. You could turn up from the x-axis. In math, it's not like physics where you say north of blah, blah, blah. We don't do that, okay? We always start from the positive x-axis. That's always the starting point, 100% of the time, whole worldwide. Always start from the positive x-axis. If you turn up, that is a positive theta. Now, despite the fact you usually do the turn first, in the coordinates, it's actually second. That's weird. Then you could go forward. Now that's a positive R. If I go forward, it's a positive R. If I turn up, it's a positive theta. I could get to any point then by turning up and going forward. You follow? I could get to this same point by turning down and then going forward. Now, if I turn down and go forward, then that is a negative theta because I turned down from the x-axis, but still a positive r because I went forward. Another way to get to this point in space is not to face that direction at all, but to face opposite that point and then back up. If I, oops, that's not what I wanted to do. Darn it. Okay, oh well. This, did I turn up or down? I turned down. I didn't mean to do that next, but oh well. If I turn down but back up, then that's a negative r, a negative theta. The last possibility is to face the wrong direction by turning up and facing the wrong direction and then backing up. So I can turn up, back up. If I turn up, that is theta positive or negative. Theta is positive, but if I back up, then r is negative. Okay, so there are four possibilities based on positives and negatives, combinations of r's and theta. You need to be able to work with all. Now, last year I said just complete this table, and it was disastrous because they were a little rusty. So let me model the thought process, and then I'll throw you to the wolves. Say I gave you the point -2, 7. Let's draw a little picture there, shall we? -2, 7 is left 2, up 7. Okay, now I want to give the polar coordinates to that. Positive r, positive theta would be to turn this way, yeah? And then go forward. How do you find r? Pythagorean theorem. 7 squared plus 2 squared equals the square root of 53. Now the good news is that's going to be the length every time, whether it be positive or backing up negative. The 53 or 7-ish item won't change. I'm always going to have to travel a little more than 7 units. You follow? All right. By far the hard part is the angles. Now, I can't find this positive angle until I know alpha, the triangle angle. How would you find alpha? Inverse tangent of, now I would ignore the signs because that's going to give you arctangent and limit you and give you positive. So just arctangent of 7 over 2. Forget the signs, okay? I think if I remember right, that was 1.292. Let's just call it 1.3 because my table is not very big, all right? Now that's radians, obviously, not degrees. 1.3 radians, probably 7 degrees or so. All right, you follow? Now, what is the polar angle you'd have to turn then? Pi minus, I'll call that alpha for the sake of it. Pi minus alpha for the positive. What about the negative version? Pi plus alpha, and it would be negative pi plus alpha because it's in the negative direction, the going down version, right? You follow? It's alpha beyond pi. Okay? What about the negative direction? Now that is facing the opposite way. What's one possible angle I could get by turning up and going in? Think vertical angles. This is alpha, so that would correspond to this is alpha. So what's that? 2 pi to go all the way around, but take away alpha because I'm not going all the way around. You follow? The last version is to face the opposite direction by going down. What is that negative angle we get by going down? Negative alpha. Check? Okay, let's do a reference triangle without a calculator, shall we? 3 root 3 over 2 is this guy, 3 root 3 over 2. Boom. Negative 3 halves. Boom. That's the point I'm trying to get to. If it says no calculator, it must be a reference triangle is what I was looking for. A reference triangle. What kind of triangle is this? 30, 60, 90 or 45, 45, 90? 30, 60, 90. A normal 30, 60, 90 or a little beefed up 30, 60, 90? Isn't a normal 30, 60, 90 just root 3 over 2 and 1/2 and 1? This looks like it's multiplied by a factor of just 3, right? It's okay, Eric. I'm glad you're giving it a go. Okay, so it's multiplied by, because if I think unit circle, right? The unit circle normally has a hypotenuse of 1. This has a hypotenuse of 3. You like the word hypotenuse? Okay, so it has a hypotenuse of 3, so I could get there by positives forward or negatives backward. You remember that? Are we cool? Okay, what's the alpha here? Is this a 30, a 60, a 45, a pi over 4, pi over 6? Pi over 6. Okay, pi over 6. Alpha is pi over 6. So one version is to turn up and go all the way around. What's the positive theta version? 11 pi over 6. The quicker way would be to go turn down. What's that? Negative pi over 6. Another possibility is in the exact opposite quadrant, where we're going to back up. Okay? To get to that direction, I could turn up or down. What's the up version? 5 pi over 6 up, then back up into the fourth quadrant, or down 7 pi over 6. That would also put me in the fourth quadrant. Are we cool? Okay. Does that get you rolling? Should we do one more row, or you got it? Okay. This time I'm giving you 2 pi over 6. I'm visual, so it helps me to graph this. This is the picture. 2 out and pi over 6. In my mind, I tie this to a normal reference triangle. A normal reference triangle is 1 root 3 over 2 and 1/2, yeah? But the one they're giving me is multiplied by a factor of 2. So instead of the x being root 3 over 2, it's root 3. Now, if you don't like that similar triangle idea, then use trig. Pi over 6, if you want x, when you have pi over 6 as an angle and 2 as a hypotenuse, then just use SOHCAHTOA. What's the y? 1. All right. Now, the others are other polar angles. So what are the radii going to be here? They're r's. 2 and negatives for backing up. For the forward direction, we've already talked about going up and going forward. That's given. So our other possibility is going down and going forward. If what's the same as going up, pipes? Down 11 pi over 6. You could also do -2's, which means backing up. If I back up, then I could get to that direction in two ways. What's going up? 7 pi over 6. And what's going down? -5 pi over 6. All right. Try the other 3 rows, and I will follow behind you and do them myself in a second. Okay, that next row by yourself? Let's see. Oh, nope. I forgot I was backing up, didn't I? Sorry. I screwed that last one. Yeah. That's a negative pi. Oh, yes, yes. It was supposed to be negative. Absolutely, yes. I screwed that up. Sorry about that. That last row was supposed to be negative. This should be -7 pi over 4 to be consistent with the table. Sorry about that. Da, 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 da. This guy is purple. this would be negative 2, correct? And if this is 2, okay, I guess I could go this or this. So multiplies by a factor of 2. So it feels like negative root 2, negative root 2. Yes? Do you agree? Yes? No? Okay. Okie dokie. Would you then go to the side and graph the first 3 on this graph, but the 4th one you should probably make your own graph. Locate those points, call A, B, and C, so you don't have to write the whole. Locate those on the photograph. How are we doing? Okay.
On D, if you go negative angle, right, wouldn't you get to like positive?
Oh, I didn't back up.
Yeah.
Right. I did the negative angle, but I didn't back up. So you're right. That should be here. Absolutely right. 100%. Start up. That should be good. Okay? Okay, moving on. Okay, besides points, let's talk basic substitution facts. You need to be able to translate from one form to the other. To make that jump, this picture rules all. Draw a beautiful right triangle on the coordinate plane. Label the components x, y, r, and theta. If you have 4 substitution facts that all flow from this picture, you can make any substitution you like, though some require a little bit of technique that we'll learn. What's one relationship between x, y, and r? Pythagorean theorem. X squared plus y squared equals r squared. Would you write yourself a note here? Sometimes to get r squared, multiply by r. That'll make more sense in a minute. Just bear with me. Okay. What is an x, y, theta relationship? Tangent theta equals y over x, or I guess you could say theta is inverse tangent of y over x, whichever you prefer. What is an xr theta relationship? cosine. Now, you could start at cosine theta is adjacent x over hypotenuse r, but the fact you really want to get down in your head is r equals, or x equals r cosine theta. Those of you physics students, you probably know that the horizontal component to a vector is the magnitude of the vector times the horizontal. To get that cosine. Yeah. The sine of theta is y over r, so y is r sine theta. The vertical component to a vector is the magnitude of the vector times the sine of the angle. Okay? With those four facts, you can easily make jumps from one form to the other. If you wanted to convert y equals 2x plus 3 to polar, then you could sub in for y with r sine theta, and for x with r cosine theta. It is common and pretty much universal that you solve for r, if possible. So if I solve for r, then r, if I move everything to one side, factor out the greatest common factor and divide back over, r is 3 over sine theta minus 2 cosine theta. Okay. And I do not take for granted that you can do all that algebra mentally with no error. I love that. R equals 3 cosine theta. That's a bit of a gimmick question because that's got a technique to it. Now, R could be sub for, and it's fine here, but that's ugly. But what's better is if instead of R, it was, no, R squared. Is what I was shooting for. Likewise, the right side of cosine is okay, but what's better than cosine? R cosine. So how could I make, if I just multiply both sides by R, I get r squared equals 3 r cosine theta. Now that serves purposes on two sides. The left side's a little cleaner, doesn't have the root, and the right side is just straight up x. That then starts to look familiar. That's the equation of a, or not. Sure, it's just, we could put it in standard form, and you'd see the radius is 1.5, and the center is 1.5, 0. But we'll talk about that in a second. Okay, you with me? All right. Let's talk basic graphs. At the end of this, if I can get through this, how much you'll be able to graph 3 types of circle, spirals, and lines. All right, so here we go. First one, I believe I have something here on your paper, r equals 3. Okay. One of the hardest things to teach in Algebra 1 is you teach kids y equals mx plus b for weeks and weeks and weeks. And then you say, okay, say we're going to graph x equals 1. And then everything goes haywire. And they freak out. I can't graph that. There's no y. What do I do? If there's no y, what can y be? Not nothing, quite the opposite. Anything. Y could be whatever it wants. Wait a second. Can y be 0? Sure, as long as x is 1. Could y be 1? Sure, as long as x is 1. Can y be 2? Sure, as long as x is 1. So here, r equals 3. So what can theta be? Anything it wants. So theta can be 0? Sure. R's got to be 3. Can theta be pi over 6? Sure. R's got to be 3. Wherever you go, wherever you turn, R's got to be 3. And so you get a circle. Now, R equals a constant. I'll use it A. For whatever reason, you just usually see A, not C. But R equals A is a circle centered at the origin. And I know it seems redundant, but bear with me. The A is the radius. So if R equals 5, then the radius equals 5. And if R equals 7, the radius equals 7. Easy, you know. Now, consider R equal, what is it, 4 cosine? Do I have? Okay, 4 cosine theta. Now, I want to get a graph of this by showing enough points to get the graph accurately, but without wasting my time. So I'll try and boil it down here. What about 0? When theta is 0, cosine is 1, so radius is 4. At root 3 over 2, I'm going to get 4, or sorry, pi over 6, excuse me, I'm done. Pi over 6 isn't the cosine root 3 over 2. And I told you up there, you're kind of going to need to know this, but root 3 over 2 is about 0.9. So what's 4 times 0.9? 3.6. So by turning that, we went from cosine's greatest value to a little less, so we're not as far out from the origin. I could go to pi over 4. Now that would be 4 times root 2 over 2. Root 2 over 2 is about 0.7. So 4 times 0.7 is 2.8. Now you can see that as we turn, cosine's getting smaller, so r is getting smaller. And if r is getting smaller, I'm moving in towards the origin. At pi over, let's go to pi over 3. At pi over 3, cosine is 1/2, so 4 times 1/2 is 2. And at pi over 2, 0. I'm into the origin. If r is 0, then I'm not moving. I'm facing in a direction, but I'm staying still. Okay? What about at 2 pi over 3? Cosine is negative 1/2. 4 times negative 1/2 is negative 2. When I face this, I go negative 2, which means I go backward 2. When I face 2 pi over 3, r is negative, and if r is negative, I go backwards. That puts me in the 4th quadrant. Here, I think you'll see that this would be negative 2.8, because you get a negative root 2 over 2, which is negative 0.7. Negative 2.8 means I back up 2.8. Then I'd get a negative 3.6. And then finally at pi, r would be negative 4. That puts me right back to where I started. Now if I kept going from pi to 2 pi, I'd start to get these same points again. So I'd get a second circle right on top of the first circle. It really wouldn't yield much. So we could conclude that r equals cosine theta is a circle symmetric at the x-axis. That makes sense. Cosine is an x-related item. And a isn't the radius. A, or the 4 here, you can see that wasn't the radius. It was the diameter. You follow? So in the next one, r equals, what is it? 1 sine? 20 sine. Oh, sorry. Okay, surely we'll have to change the scale. Do you want to go by, let's go by 5, shall we? Okay, this time I think I'm going to shorten it just to the pi over 4. At 0, what sign? So it's off. 0. At pi over 4, what sign? Which is 0.7 times 20. 20 times 0.7, 14. Okay, so 5, 10, a little shy of 3 rings to get to 14, yeah? At pi over 2, what sign? Sine of pi over 2 is 1 times 20, that is 20. Now, in the previous graph, I had some backing up action. What about at sine of 3 pi over 4? Is sine negative and causing me to back up, or is sine still positive? Still positive, so I'm still going to go positive. That would be positive 14, and then back to 0. I could go from pi over 2 to 2 pi. Those would be negative signs, and those would be backing up points. But again, you get the same shape. So r equals a sine theta is a circle symmetric at the y-axis, and a is the diameter. Now the whole goal then, by getting you these equations, you do the graphs by recognize the equation. Just like when I give you a parabola now, you don't plot a bunch of points, you just know what to expect and you graph the shape. If I give you r equals 9 cosine theta, I would say, well, I need to go out to 9, so maybe go by 3s, and I know it's a circle symmetric at the x-axis. Boom, done. There's no table. You just know the shape, right? Right? Okay. So with time, you'll get those in your brain, and those will be 3-second graphs. Okay, what the heck is going on? What is the deal? Kendall, what did you do? All right, spirals, here we go. In order to spiral out, how would I do it in a polar way? You want, as you turn, to go further and further out, right? So don't they need to just be tied directly to each other? So what should I do? Let's go R equal theta. Now, for this, remember pi, besides being a whole kit and caboodle of angle stuff, pi is also 3.14159. Because it seems people forget that here. When theta equals 0, what's R? 0. Let's go here. When theta is pi over 4, R is pi over 4. But how do I go forward pi over 4? It's probably better to think of pi over 4 is about 3/4. So when I face pi over 4, I'm going to go forward about 3/4. At pi over 2, I'm going to go R of pi over 2. But that needs to be made an actual number I can go. So pi over 2 is about 1.57, yeah? So when I face pi over 2, I'm going to go forward about 1.57. When I face pi, I would go forward about 3-ish units. Now when you do a spiral, I want you to be accurate at all the quadrantals, or the axes. So the next one is 3 pi over 2, which is about 4.5, right? 9.5-ish. 4.5, though, is off the graph. Now the minute you've gone off the graph, that's when you're done. I don't expect you to keep going, but you have to graph it. So R equals 8, theta is a spiral. Okay, that should get you started. Have a lovely day. Go finish the notes. All right? This lesson took a lot longer than I thought it would. Hopefully no one's Eric. He's giving it a go. I wish I had an Eric and AJ podcast. Those turkeys say absolutely nothing. They are what's your name?
You didn't talk about the tree.
I did not talk about the tree.
All the work we put into the tree.
I guess I didn't understand. I thought I was supposed to talk to AB about it.
Yeah, I thought that was AB. I was looking at that all us.
It says talk AB this, which is to me just terrible English to talk to AB calculus about. But I didn't talk to them either, so it doesn't. All right. Have a lovely day.
What can we know now?
We were supposed to talk about. I don't know what we were supposed to talk about.
We're getting a Christmas tree.
Oh, we're gonna get a Christmas tree in here
And
and all
everyone's
that.
donating $1. Aww.
Yeah, that would be great. You don't have any senior pictures?
Well, I submitted the one to the
I'll
yearbook,
get a
but
different one.
I don't want to order. I don't want to spend
charge
money
you everything
on
here.
ordering
That's
pictures
what I-
because that requires spending money.
What, don't your folks want to see the pictures of you? They see it every day. What if you get hit by a bus? What they want pictures? Just bring up sad memories?
No, those should be like that ugly.
No, they wouldn't.